So in this video, we're going to be talking about the electric potential energy. Now, electric potential and electric potential energy, they are not the same, all right? And we're going to see the difference in this video. Now, the electric potential energy is the work done by a unit positive charge in an electric field. The work done by a charge, all right, or the energy used up by a positive charge in an electric field is what we call the electric potential energy. Now each symbol is U. All right, this is a symbol. We can have U or we can have W. Now it is measured in joules or electron volts. So the electric potential energy can be measured in joules. It can also be measured in electron volts. Now to convert from electron volt to joules, we use this conversion factor. 1 electron volt is equal to 1.6 times 10 raised to the power of minus 19 joules. So this is the conversion factor we use whenever we want to convert between electron volts and joules. All right. So what then is the equation for electric potential energy? Now energy is equivalent to work done. All right. We said electric potential energy is simply the work done. So that means mathematically that electric potential energy is equal to work done. And then we know that work done is equal to force times distance. So we can say electric potential energy is simply force times distance. From Coulomb's law, we also know that force between charges or between 2-point charges is equal to K Q1 Q2 all over R squared. All right. So this is now going to be, rather than writing F, we can write KQ1 Q2 over R squared multiplied by the distance. All right. So now this is going to cancel this, and then you're going to have potential energy equals KQ1 Q2 all over R. So this is the equation we use for calculating electric potential energy. But this is applicable when we have a pair of charges. Electric potential energy for a pair of charges. Electric potential energy for a pair of charges. So when you have a single charge, what then is going to be your equation? Don't forget U is still the same as W. If you don't have U, you can also have W equals KQ1 over KQ1 Q2 over R. All right. Don't forget to use this to calculate electric potential energy for a pair of charges. So when it's now a single charge, what is going to be your equation? From this equation, we have that U is equal to KQ1 Q2 all over R. This is what we have here. This can further be simplified to U equals KQ1 all over R times Q2. All right. So if we have a single charge, all you just need to understand is that the whole of this is electric potential. Electric potential is equal to KQ over R. That's the equation for electric potential. So rather than writing KQ over R, we can change it to V. V is the unit for electric potential. So we're going to have V times Q. So for a single charge, electric potential energy is equal to V times Q. So this is another equation you can use. You can write it as U equals QV. Electric potential energy rather. Alright. So electric potential energy is equal to electric potential times charge. You can have it as U equals QV. Alright. So this is your equation for electric potential energy. You can work with this or you can work with this. But this is applicable for a pair of charges, and then this is applicable for a single charge. So now we are going to see the application of these equations. All right. Everything I've stated so far are very, very important as long as electric potential energy is concerned. Okay, for this question, it says determine the electrostatic potential energy due to two charged bodies with charges of 15 microcoulomb and 25 microcoulomb separated by a distance of 10 cm. So we have two charges, charge 1 being 15 microcoulomb and then charge 2 being 25 microcoulomb, and the distance between them is 10 cm. All right. So now remember, whenever we have a pair of charges, the formula for our electric potential energy or electrostatic potential energy is giving us U equals KQ1 Q1 Q2 all over R. All right, and Q1 is equal to 15 times 10 raised to power minus 6 coulomb. Q2 is 25 times 10 raised to power minus 6 coulomb. All right, micro means 10 raised to power minus 6. And then 10 centimeter to meter. To convert from centimeter to meter, you divide by 100, and this is equal to 0.1 meter. All right, so to simplify this, we simply plug in our values. K is a constant, and K is always equal to 9 times 10 raised to power 9. So we're going to have 9 times 10 raised to power 9 times Q1 is equal to 15 times 10 raised to power minus 6. So we have multiplied by 15 times 10 raised to power minus 6 times Q2 is 25 times 10 raised to power minus 6 all over R, which is 0.1. So we're going to have electric potential energy equals, and that will give us 33.75 joules. So this is our answer in joules. Electric potential energy measured in joules. Now the next question here says calculate the work done by an electron in a field which has a potential, all right, of 4.5 volts. So they gave us potential to be 4.5 volts, and we're talking about work done by an electron. The charge of an electron is a constant and is equal to 1.6 times 10 raised to the power of minus 19 coulombs. We are asked to calculate the work done, all right, which is still the same as the electric potential energy. Work done and charge, they are equal or equivalent to each other. All right, so we're looking for U and we're given a single charge. Now they say express your answer in electron volts. That's say after getting your electric potential energy, you need to convert it to electron volts. All right, so now let's go ahead and solve for the energy first, or the work done. So we can say our electric potential energy, remember, for a single charge is equal to Q times V. All right, that's the charge times the potential, or potential difference. So we have Q being 1.6 times 10 raised to the power of minus 19 multiplied by V. V is the electric potential, which is 4.5. So we have electric potential energy to be 1.6 times 10 to the power of minus 19 multiplied by 4.5, and that will give us 7.2 times 10 raised to the power of minus 19 joules. So this is our value for electric potential energy in joules. Now to convert it to electron volts, we simply use the conversion factor. 1 electron volt equals 1.6 times 10 raised to the power of minus 19 joules. Minus 19 joules. All right, so to convert this to electron volts, we can simply say X electron volts equals 7.2 times 10 raised to the power of minus 19 joules. So we cross multiply here. So this times this, that will give us 1.6 times 10 raised to the power of minus 19 times X, that will give us 1.6 times 10 raised to the power of minus 19x equals 7.2 times 10 raised to the power of minus 19 times 1. That will give us 7.2 times 10 to the power of minus 19. So to get our answer in electron volts, which is X, we divide both sides by 1.6 times 10 to the power of minus 19. So we have 1.6 times 10 raised to the power of minus 19x all over 1.6 times 10 raised to the power of minus 19 equals 7.2 times 10 to the power of minus 19 all over 1.6 times 10 to the power of minus 19. The whole of this will cancel this. Then you're going to have your final answer in electron volts to be 7.2 times 10 raised to the power minus 19 divided by, we have 1.6 times 10 to the power of minus 19. And that will give us 4.5 electron volts. Now, our next question here says if the electric potential difference between 2 points is 42 volts. All right, so we have potential difference here to be 42 volts. They say what is the work done by an agent? So we are looking for work done, all right, by an agent in moving a charge. We have charge to be 5 times 10 raised to the power of minus 6 coulomb from one point to the other at a constant speed. So they gave us V, we're looking for W, and they give us Q also. Don't forget W is still the same thing as the electric potential energy. Work done and energy, they are equivalent or equal to each other. So we can just say W is equal to QV, just like we usually say U equals QV. You can say W equals QV. Now Q is 42, so we have, sorry. Now Q is 5 times 10 to the power of minus 6 multiplied by V, which is 42, and that will give us 2.1 times 10 raised to the power of minus 4 joules, which is option C. Now question 4 says the potential difference required to give a helium nucleus. All right, this is a charge for a helium nucleus. They gave it to us to be 3.2 times 10 raised to the power of minus 19 joules, sorry, coulombs. 3.2 times 10 raised to the power minus 19 coulombs. 48 times 10 raised to the power 3 electron volts of kinetic energy. So they gave us the energy to be 48 times 10 raised to the power 3 electron volts. Is, they say the potential difference. We're looking for the potential difference, V. All right. So to calculate this, we use our equation U equals QV, and V will be equal to the energy all over the charge. By the time we make V subject of the formula, V will be equal to U over charge, the energy over charge. So this is what we're going to use. But before we plug in our value for energy, we need to convert it to joules. All right. They gave it to us in electron volts. All right. So to convert energy to joules, we simply say 1 electron volts equals 1.6 times 10 raised to the power minus 19 joules. This is the standard, and this is what we want to convert. So say 48 times 10 raised to the power 3 electron volts is equal to X. So cross multiply, all right. X times 1, that will give us X equals the whole of this times this. So we have 48 times 10 raised to the power 3 multiplied by 1.6 times 10 raised to the power of minus 19. So that will give us our energy in joules to be, we have 7.68 times 10 raised to the power of minus 15 joules, right? So this is the energy in joules. Now the electric potential, now the potential difference, we can now substitute our values. The energy is 7.68 times 10 raised to the power of minus 15 all over the charge, which is 3.2 times 10 raised to the power of minus 19. That will give us the potential difference to be 24,000 volts, all right, which is equivalent to 2.4 times 10 raised to the power 4 volts, and that is option A. All right, so moving on, question 5 here says a charge Q1 equals 9 microcoulomb is located at the origin, and the second charge Q2, which is 1 microcoulomb, is located on the x-axis at x equals 0.7 meter. So basically we have two charges, charge 1 and then charge 2 is on the x-axis. All right, so we have charge 2, charge 1. X is horizontal and this is positive x-axis, so it's to move towards this way. So we have 0.7 meter. So it simply means from charge 2, the distance between charge 2 and charge 1 is 0.7. So we can see our distance of separation between the two of them is 0.7 meter. They say calculate the electric potential energy for this pair of charges. So we are looking for U. All right, again, we have a pair of charges. So our equation will be U equals K, right? This is Q2, K, Q1, Q2 all over R. This equation whenever we want to calculate electric potential energy for a pair of charges. All right, Q1 is 9 times 10 raised to the power of minus 6 coulombs. Q2 is 1 times 10 raised to the power of minus 6 coulombs. So we just plug in our values. We have K to be 9 times 10 raised to the power 9 multiplied by Q1, which is 9 times 10 raised to the power minus 6 multiplied by Q2, which is 1 times 10 raised to the power of minus 6 all over the distance, which is 0.7. So at this point, the electric potential energy is going to be, so using our calculator, our final answer becomes 0.116 joules. Okay, so with this, we've come to the end of this video. Please do not forget to smash the like button and also subscribe to the channel, and also share this video with your friends and your colleagues.